Hello, welcome to today's maths tutorial video where we're going to be looking at quite an important topic because we're looking at quadratic inequalities, how to solve them. And I'm calling it quite an important topic because it's one for which the steps are individually actually quite easy to do, yet a lot of students get these questions wrong due to a lack of understanding about what you can and can't do with inequalities. So let's hopefully solve that issue by explaining things today. To get to the root cause of that though, I think we need to start by taking a trip back to inequality stuff that you've done before. So for instance, I'm expecting that in your previous maths education, you've come across solving inequalities that look like this. Ultimately, all you've got to do for very, very simple inequalities like this is ultimately solve them similar to how you would solve an equation by doing operations to both sides. So for instance, we could start off by taking away 5 from both sides to get minus 3x on the left and 21 on the right. But then also just one extra thing you have to consider, which is whether the inequality sign will stay the same or flip around depending on what operation you chose to do to both sides. For instance, that first operation we did was take away 5 from both sides, and that has no effect on the inequality sign, so we keep it the same. We can then also, next step, divide both sides by minus 3 to get the x by itself. 21 divided by minus 3 is minus 7, but this time we've got to watch out. Because we chose to divide both sides by a negative number, we must remember that's one of the operations that causes the inequality sign to change directions. And therefore the final answer is x is greater or equal to minus 7, and it really is as easy as that. Just solve the equation like normal, but then just sometimes have to consider whether you keep the inequality sign the same way it was before or whether it flips around. However, watch out, because we do need to be very aware of which operations do cause the inequality sign to flip around and which ones don't. For instance, the operations that cause the inequality sign to stay exactly the same are the situations where we add anything we like to both sides, or if we subtract anything we like from both sides. Multiplying also works, but only if we multiply by specifically a positive number. And then the same goes for dividing. As long as we divide by a positive number, the inequality sign stays exactly the same as it was in the previous step. And then there's also those operations that cause the inequality sign to flip around. And just so you're aware, those operations are when we times by a negative number, or as we just saw in the previous example, if we choose to divide by a negative number. The problem is that this is pretty much the vast majority of the operations we can do to an inequality while still knowing what's going to happen to the inequality sign. Which is a bit of a problem, because if we're trying to solve more complicated inequalities where we have to use more complicated operations, we might be trying to do those operations, yet we don't know what's going to happen to the inequality sign. You might notice, for instance, we're missing lots of operations off this list. Squaring is not on this list. Using square rooting to undo a squared is not on this list. And then there's also a whole bunch of new operations that we're going to be learning about as part of Maths A-level that are also not on this list. And therefore, those are all operations that if you need to use as part of solving the inequality, that means you cannot and should not try to use the approach we showed before to solve the inequality, because the more complicated the operation means you cannot keep track about whether the inequality sign should be staying the same or flipping around in the other direction. Admittedly, those of you who have covered more maths and are looking back at this video for revision purposes, there is technically another common operation for which there is a predictable effect applied to the inequality sign, which is taking logarithms of both sides as long as the logarithm has a base bigger than 1. However, as most of the people watching this video probably haven't covered logarithms yet, don't worry about it, and I'm just including it in this list here for the sake of completeness. But reiterating one more time, if you want to solve an inequality using an operation that's not on the list on the screen right now, don't try to treat the inequality like an equation and just try and solve it like normal and just do some occasional adjustments to the inequality sign, because it won't work that way. And that is also true, therefore, for quadratic inequalities. The reason for that is it doesn't matter what method you use for solving a quadratic inequality, whatever method you use for solving quadratics in general, you are going to be using an operation that wasn't included in that list we had on the previous slide. For instance, if you use factorizing to solve a quadratic, then at the point where you get from having the factorized brackets to the individual solutions, you end up having to divide by one of those brackets, and the problem is those brackets have algebra in them. And the problem is, in that previous slide, I was very specific and said you could only divide by positive numbers or divide by negative numbers. The problem is algebra is not a positive number and is not a negative number. It is an uncertain value currently, and therefore you cannot divide by something with algebra in it and expect to know what's going to happen to the inequality sign. Or alternatively, you could have tried solving the quadratic using the quadratic formula, but the quadratic formula includes a square root, which is there partly to undo the squared symbol that appears in quadratics, and therefore square rooting wasn't one of the operations I included on my list on the previous slide. So again, we don't know how to deal with that while solving the equation and trying to deal with the inequality sign at the same time. So now we've got our heads around the fact that we can't continue solving inequalities like we were before. Be aware there's a new approach we have to take to things. To solve quadratic inequalities, for instance, the first step is you're going to find critical values. Those are the numbers that are going to appear in the final answer next to the inequality signs, but we're just interested initially in just finding what those numbers are and not interested in finding the inequality signs at all. And to do that, that's what we're going to do by solving it like an equation. But there's a few details we'll have to watch out for with that you'll see when I get onto an example. And then the second stage is then using a graph to separately decide what's going to happen to the inequality signs. Because as I said, the solving the inequality like an equation is not going to give us any information about what the inequality sign should become when you reach the final answer. So we need some other extra information like a graph in order to help us do that. Now, it's worth mentioning on the internet you might find some other alternative methods for solving inequalities, and some of those other methods will work, but I am very much a promoter of the use of graphs to solve things, and that's because actually the act of drawing the graph will often be quicker than the act of using more numerical methods that people have for solving these things, or algebraic methods for solving these things, which will get you the correct answer but will require a lot more writing than a single graph, which just by itself already tells you a lot of information visually. So those are the two main stages. Therefore, let's have a go at doing examples so you can start to see what needs to be done to do these things. So example 1, I am going to have lots of examples in this video, so if it's a bit overkill, apologies in advance, but I just want to show you all the ins and outs and things to watch out for so that you get a good solid understanding of what you are and aren't allowed to do. So step 1 for solving a quadratic inequality is to find what we call critical values. I'm going to write the title critical values. You won't get marked on that, but it doesn't hurt to write it because, hey, you're indicating to the person reading what you're trying to find at that particular stage, and then also explains why we're doing the next step, because this next step at first glance does appear illegal. What we're going to do is we're going to rewrite the inequality as an equation. And the reason we're doing that is because we're fully acknowledging the fact that we're aware that we're not solving the question they're asking us to solve yet. We have written critical values because we're pointing out that's all we're trying to find at the moment yet. We're not actually trying to solve the inequality, we're just trying to find critical values, which will help us solve the inequality, but we're not actually dealing with the inequality part yet. So that's why I'm writing an equals at this stage, to then partly make that clear that I'm aware we're not trying to solve the inequality yet, because we don't know what's going to happen to the inequality sign when we do the steps we're about to do to solve this equation. So solve this equation however you like. It is one that's very easy to factorize, so I'm going to do that. Solve the quadratic from that point by technically you're dividing both sides by x minus 1 to get x minus 3 equals 0, which leads to the solution x equals 3. But because we divide by algebra, that's why we wouldn't have known what's going on with the inequality sign. Alternatively, take a step back and divide both sides by x minus 3 to get x minus 1 equals 0, which leads to x equals 1. Okay, what have we found? We've found the numbers that will appear in the final answer, but we haven't dealt with the inequality signs, and that's where we're now going to move on to stage 2, which is to draw a graph. What have you got to do? Well, you've got to draw a graph of y equals both of the individual sides of the inequality. So therefore, I am going to draw y equals the quadratic that's appearing on the left-hand side of this inequality, and I'm also going to draw y equals the 0, which is, in this case, what's on the right-hand side of the inequality. So you're drawing y equals both individual sides of the inequality. So how are we going to get that done? Well, we've got to use the graph drawing skills we've looked at before. So to draw the graph of the quadratic, we need to know the x-intercepts. Good news, we've already worked them out as part of finding the critical values. We also need to know what the y-intercept is, but we can tell already that's 3. We also can tell it's a positive quadratic shape. So putting that all together, we know the quadratic will look something like this, a positive U shape. And then, of course, putting on some axes so we can start marking on our x-intercepts. And then also we know where the y-intercept is as well. Cool, I've sketched my quadratic. I'm then also going to sketch the line y equals 0, and in this case the line y equals 0 is just, funny enough, the x-axis. Technically, because we've already drawn the x-axis, I'm not needing to draw another line on top of it, but I have just done it in this case to make the point that every single time you're solving an inequality like this, when you come to draw the graph, you're drawing y equals both sides of the graph. Okay, but then what do you do with the graph? How is it helpful to then decide what is the final answer with the inequality signs? Well, you've got to do the following things. You've got to use the y values of the graph to first of all decide which part of the graph is needed. In other words, which parts of the graphs are above each other or below each other, depending on what the original question is asking. That's difficult to describe in words. You'll see what I mean when we go back and look at the example again. And then once you've decided which part of the graph is the important part, you're then going to be looking at the x values for that part of the graph you've chosen to then decide whether we should be talking about less than or greater than the critical values we had before. Again, difficult to describe in words. You'll see what I mean when we look at the example. So now that we have explained that, how does that work in practice? Well, as I said, you first start off by deciding what part of the graph you need by looking at the y values. And that's why I wrote y equals above both sides before, to kind of indicate what we're about to do. Because what we're going to see is we're looking for where the y values of this thing are less than the y values of this thing. In other words, where is the quadratic below the x-axis, because y values that are less than other y values means they're below, because smaller y values are lower down on a graph. So in this particular case, we're asking where is the quadratic curve below the x-axis. So you look at our graph and we realize it's this region of the graph here. This is the bit we want here. So therefore, what does that mean when we want to write the final answer? Well, all we've got to do now is we use the y values to decide which part of the graph we wanted, but now we're going to look at the x values for the part of the graph we chose to realize what the inequality signs are going to be in our final answer. Because looking at this bit of the graph we've chosen, we realize if we look from left to right, all these values that we've highlighted are to the right of x equals 1, but they're all to the left of x equals 3. So that means all those x values are x values that are greater than 1, because if they're to the right on a number line of an x value, that means they're greater than. But if they're to the left of 3, that means they're still less than 3. So the final answer is 1 is less than x is less than 3, because all the x values are in that inequality region. Cool. That's how you solve a quadratic inequality. Okay, let's take a look at some more examples, because this will give you the chance to show that the general structure and idea of approaching these problems stays the same. There are some small things you do have to watch out for when you're doing this, but that's just a case of adapting to what the algebra tells you and what the graphs tell you. The steps and approaches you're doing stay the same. So for instance, for this one, we've got another quadratic with an inequality sign. So we start off by writing critical values, rewriting the inequality as an equation to acknowledge that we're aware that we're not solving the inequality yet. We're only trying to find the numbers that will be important at the end. And this time I'm going to solve using the quadratic formula because not all quadratics are nice to solve. Not all of them are possible to factorize. That's all right. We've just got to use the quadratic formula. And we've got that. And then on the bottom, that'll be 2 times by 1. And then I type that into my calculator. If you type that into your calculator, apparently we get 5 plus or minus root 2. Okay, now we're going to draw the graphs. So I'm going to draw y equals the quadratic, and I'm going to draw y equals 0, as that's what's on the right-hand side. So first of all, starting with the quadratic, well again, we know it's x-intercepts because the critical value calculation happened to find that out at the same time conveniently. We also can find out that the y-intercept is positive 23 by looking at that number on the end, and we know it's going to be a positive quadratic shape because it's a positive 1 as the coefficient for the x squared. So therefore, once again, we've got this sort of U-shaped quadratic curve going on. But then when we come to drawing the rest of it, it's a bit more complicated than before just because our x-intercepts are a bit more nasty this time. We've got 5 plus or minus root 2. Logically, 5 plus root 2 is going to be the bigger number. So that one's going to be the 5 plus root 2, and that's 5 minus root 2. And actually, both those numbers are positive, though, if you look at the decimals. So actually, the graph does look very similar to last time. So therefore, we've got this going on. And then drawing on y equals 0, again, y equals 0 is just the x-axis, so I didn't really need to draw that extra line, but oh well. Again, making the point I'm always drawing the graph for the right-hand side. Okay, now we need to decide which part of the graph we need. We're looking for where the y values of the quadratic are greater than the y values of y equals 0. That's, in other words, because it's saying greater y values happen above. So therefore, we're looking for where is the quadratic curve above the x-axis. And that is 2 regions. It's this region here up to that point there. And then it's starting at this point here and continuing on forever to the right. So that's which part of the graph we want, decided by the y values. Now use the x values to decide what the final answer is. So now we're only looking left and right rather than caring about what's happening up and down. So we've decided we want this bit I've shaded there. And therefore we realize all those points are to the left of 5 minus root 2. To the left on a number line horizontally means we're going less than. So that region is going to be x is less than 5 minus root 2. And then we've also got a separate region over here, and that is all these values that are happening to the right of 5 plus root 2. So therefore that's important because if we're going to the right, that means it's greater than, so therefore x is greater than 5 plus root 2. This time, I've written the inequality answer as 2 separate inequalities, and that's because that's reflecting what I can see in the graph. On the graph this time, it was 2 separate regions rather than one big region, so that's why the answer is 2 separate inequalities, whereas last time it was one big overall inequality as the final answer. Important things to be aware of to write your final answer. You should never write the word and in between these 2 inequalities because that would be incorrect. There are no values which are in both inequalities at the same time, and in maths kind of means both happening at the same time, so to speak. So therefore we've got to leave them separate. So my biggest bit of advice is just to put a comma in between the 2 inequalities, or if you really must write a word, write the word or, but it's better to write an inequality. Some questions will also ask you to write your answer in either set notation or even perhaps interval notation, but I'll deal with showing how to give answers in that format in a separate video. Third example. So once again, you're probably getting the idea, but we start off by finding critical values. So therefore, we write the equation equals, rather than as an inequality, we solve the quadratic using whatever method we like. This, of course, is a quadratic I've definitely used in examples in other videos, because it's one we can factorize by factorizing -1 out the front and then factorizing the quadratics that's left by that. And so therefore we get the critical values x equals 2 or x equals 3. Those are just the critical values though. We've now got to draw the graph. So therefore I'm going to draw y equals the quadratic, and that will be, this time, watch out, it's going to be an upside down quadratic because the coefficient of x squared is a negative number. So that means instead of a U shape, it's a upside down U shape, something like that. Okay, we know its x-intercepts are +2 and +3. And this time the y-intercept is negative, it's -6. Okay. We're also going to draw y equals 0 again, and therefore that is the x-axis. And then we decide which part of the graph we want. This time we're looking for where is the quadratic greater or equal to y equals 0, which is saying if we're looking for y values that are greater than, we're looking for above. So we're asking where is the quadratic above the line y equals 0. So we're looking for where is the curve above the x-axis. So therefore we want this region here. Cool. Use the y values to decide which part of the graph to shade, then use the x values to decide what happens to the inequalities. And this time you'll notice it's all the values starting at 2, finishing at 3. So therefore it's x values to the right of 2, so x is greater or equal to 2, and it's still though all the way up until it stops at 3, so its x is less than or equal to 3. One big inequality because it's only one region on the graph. Also worth noting, this time the question had a greater or equal to symbol in, and that's why my final answer had less than or equal to inequalities in. The inequalities are including the equal part, and that's just because of that equals part appearing in the inequality sign in the question as well. So that thing is something to watch out for. You've got to adapt what sort of inequality signs you use, depending on what the original question was asking partly. And on to the fourth example. This time it looks a bit more scary because there's something other than a 0 on the right hand side. Ooh. However, the method I've told you still carries on. So we still start by finding critical values by rewriting the inequality as an equation. Using whatever method we need to usually use to solve an equation like that, which is, well, we can't solve anything that's a quadratic until it's equal to 0. So we've now got to rearrange it to make it equal to 0. Then solving that quadratic as we normally would. This time, again, using quadratic formula because I can tell looking at it, it doesn't look very nice to factorize. And if we type that into the calculator, we'll get -3 plus or minus 3 root 5 all over 2. There you go. So we've solved the quadratic even though it was rather horrible answers. So now we've got to draw the graph. Now admittedly you do have a few choices when you get to this stage for this question, because you could draw a similar sort of style of graph to what we had before, because you notice at one point in the working we do reach this point where we've got a quadratic and it equals 0 on the other side. However, if you want to do it that way, you would have had to have kept track of what happened to the inequality sign up to this point, which is still possible to do because getting to that point, we only were adding and taking away stuff. And at the beginning of the video, you might remember that I did point out that adding anything you like or taking away anything you like is one of the actions we can do that still maintains the inequality sign. It's the stuff after that that is the point at which we can no longer keep track of the inequality signs because we're doing actions that weren't on that list of legal operations that we can use when trying to deal with an inequality sign. But instead, to just show you the overarching theory behind the method we've shown already and to show that it applies beyond even the things we've dealt with so far, you can still do what we were doing before, which is just draw y equals the two individual graphs on the individual sides of the original question. So I'm going to draw y equals x squared plus 4x minus 5. That will be a quadratic with a positive u shape. So therefore I can draw a positive u shape to begin with. It's going to have x-intercepts of, well, watch out, because technically I don't know that based on the information I was trying this time. I hadn't solved that quadratic when finding the critical values. So you'd have to solve x squared plus 4x minus 5 equals 0 if you want to find the x-intercepts of that. Luckily, that's very easy to do. It's just going to be x equals minus 5 and x equals 1. And then, of course, also we can draw on the y-axis. We know the y-intercept will be minus 5, and also we know the y-axis happens at x equals 0, which is between 1 and minus 5. So therefore the y-axis will be probably nearer to, well, it's definitely nearer to 1 than minus 5. So we'll draw it about there, and therefore that would be a good way of drawing it. We're now also going to draw y equals the graph that's on the right-hand side, and for the first time in this video, it's a more complicated graph. It's not a problem though, you just draw that graph. So y equals x plus 4, and luckily that's actually still quite a simple graph to draw. It's just more complicated than what we had before. And so therefore y equals x plus 4 is just a straight line with a gradient of 1. It's got a y-intercept of 4, an x-intercept of minus 4. So that means it's going to be intersecting the x-axis before the quadratic has its lower x-intercept. So therefore, if we're drawing it well, then it will look something like this. Because then we have that being 4 and we have that being minus 4. And so therefore that's important for making sure the line is in the correct position in relation to where the quadratic was placed on our graph. But now the graph looks more complicated. How are we meant to know which part of the graph we want? Well, still the logic we were saying before is what helps decide which bit of the graph you want to do. We've got the y equals the quadratic bit, and then that's appearing before a greater or equal to, and then followed by the y equals x plus 4. So it's saying we want the y values of the quadratic to be greater or equal to the y values of y equals x plus 4, and if y values are greater or equal to, that means they're above or the same. So we want the quadratic to be above the straight line y equals x plus 4. So that means, if we're looking at the graph, where is the quadratic above the straight line? It's above it for all of this region, all the way down to this point here. And then it's also above the straight line from this point onwards as well, which is at that point. Now you might be wondering what those points are. Well, you see, that is what the critical values were at. So this one down below here will be the smaller of our two critical values. And the one over here to the right would be the bigger of the two critical values. That's ultimately what you're finding when you find a critical value. You're finding the point at which something might change about the graph that might mean the graph goes from being above to going below, or goes from being below to going above again. And so that's why we had to calculate them. That's interesting because it now means still, then when we come to solve it, it's still very easy to use this graph to solve the final inequality. But as you can see, the bit we shaded on the left is all to the left of minus 3 root 5 over 2. So therefore x is less than or equal to minus 3 root 5 all over 2 as the first inequality for the first region. And then as a separate inequality, because it's a separate region on the graph, we have x is greater or equal to because it's to the right of our second critical value, the part of the graph we shaded, and therefore x is greater or equal to minus 3 plus 3 root 5 all over 2. There you go. Now the interesting knock-on effect of this is that actually, although this video was titled Quadratic Inequalities, I have now shown you effectively a method that can be used for solving almost all inequalities at A level, even if they have some very complicated algebra steps needed in order to solve the equation part of things normally. As long as you know how to solve the equation as its own separate thing, and individually know how to draw the graphs of the things involved, you can solve the inequality. There's one extra small detail I would have to add on top of this though, but we'll deal with that in a separate video, and therefore hopefully this has at least though given you a beginning idea to how this method is useful for solving inequalities. Okay, that will do us for today. I hope to see you in a future video.